Hi everyone, I'm Myung from Seoul National University and Samsung Electronics. Today, I will talk about our work, competition-based additive caching for out-of-core graph processing. The out-of-core graph engine accommodates the entire graph dataset in a single node. No matter the size, the graph dataset resides on the storage device, and the graph subset is dynamically loaded onto the memory. If cached subsets such as 1, 2, and 3 are requested by the graph algorithm, it can be retrieved without storage access. The cache improves performance by keeping data subsets that are likely to be accessed in memory, so that the graph engine can save the time to load data from the storage device. So when cache miss occurs, such as 4 in the figure, it's important to evict the right victim that won't be accessed in the near future. It's needed to make room for the newly loaded data. And the victim selection process entirely depends on the cache policy. For example, LRU policy evicts pages that have not been used recently, while MRU policy evicts the last used page. Although LRU-based policies have been commonly used, those policies at times made inadequate decisions in graph applications. Then let's see what happened when we fixedly used the clock policy, which is an approximation of LRU. As shown in the figure, a high hit ratio has been achieved in triangle counter algorithm. But the hit ratio in PageRank rarely increases to 70% of the cache size. So this figure demonstrates that one cache policy has different effectiveness depending on the graph algorithm. This results from the different data access patterns of algorithms. In terms of PageRank that has a low hit ratio with the clock policy, it's usually implemented based on the propagation model using an iterative procedure. So looking at the data access pattern shown in the figure, temporal locality rarely exists. In this case, unused pages are accessed in the near future than used pages. Therefore, it can be assumed that clock or LRU is not suitable for iterative-based graph algorithms like PageRank. On the other hand, for triangle counting, the number of accesses tends to be concentrated on some pages. This is because vertices with many edges, like the red node, will be referenced more than others while checking for potential triangles. Depending on the edge distribution inside the graph dataset, LRU or clock can perform optimally. So we thought, how can you find out the optimal policy in real time despite variable circumstances? And we made the cache scheme graph adaptive caching, which provides adaptability and high performance. Basically, we applied a competition mechanism between two contrasting policies, clock and LIFO. In order to evaluate the outcome from the competition between clock and LIFO, we apply a simple evaluation rule, which is a better policy will evict a page earlier and correctly. Let's look at an example. Policy A evicts page 1, then the page has never been accessed for a while. Then another policy B decides to evict the same page. Policy A wins because policy A selected the correct victim earlier than policy B. Let's see another example. This time, The page has been accessed before policy B decides to evict this page. This means policy A made a misprediction, and B wins. Note that both clock and LIFO can either be policy A or B for a given victim page. Evaluation results from competitions are accumulated as a score. The score starts at 0. When LIFO wins, the score is incremented, and the score is decremented when clock wins. The active policy and fallback policy depend on whether the score is positive or negative. The active policy, which is winning, physically evicts the victim, and the fallback policy, which is losing, virtually evicts the victim. Now that we understand how the active policy and fallback policy are determined, I'll explain how each policy changes the state of the pages. Each page has 4 states depending on eviction state and storage location. Let's see the life cycle of page 1. This page begins with a not cached state where the data copy exists only in external storage. Once a cache miss occurs for page 1, it is loaded onto the memory, then the page goes to the cached state. Suppose that the fallback policy virtually evicted the page 1. Then the page is tagged as virtually evicted in the metadata, but the data copy still remains in memory. The evicted state indicates that the competition for the page is in progress. Once the same page is selected by the active policy after a while, it turns out that this page has already been selected by another policy and has not been accessed in the meantime. So the fallback policy gets a score. Let's see another case. Page 2 is in cached state. Suppose that the active policy evicts page 2. Then the page frame is physically reclaimed so that a newly loaded page occupies that frame. So we need to keep the metadata as a ghost page to continue the competition process. I'll explain more about the ghost page later. If this page is referenced again, it is going to be found on the ghost list. Then the page should be reloaded to memory. The fallback policy wins again like this, because it turns out that the active policy made the wrong decision. In our cache scheme, each page belongs to a certain page group. This grouping technique alleviates the log overhead when using multithreading, and it also promotes the competition process by reducing the competition window. So when a page is requested, the cache manager visits the associated page group and traverses the pages. Then, if the page miss and group full occur simultaneously, the competition mechanism is handled within the group range. In the group, victims are selected by 2 policies in their own way. So if clock is the active policy, clock victim is actually replaced with a new page after saving the metadata to the ghost page. Metadata includes the file address of the page, the eviction policy, and timestamp. Timestamp is used for decay function to adjust the rate of competition events over time. and we don't force all groups to perform the competition procedure. Instead, we make only the sampled voter groups participate in the competition process, and the rest of the groups just follow the global policy. It significantly reduces the overhead of the competition mechanism, because worker threads are allowed not to perform competition procedure when the desired page belongs to follower groups. From now on, I'll introduce the experimental results. We used 16 threads and 2 types of SSDs in order to demonstrate the performance improvement by our scheme. Also, our scheme is implemented based on flash graph. And we experimented with 2 graph datasets and 4 graph algorithms to verify on various graph workloads. Let's see some results featuring the hit ratio. In 3 algorithms, WCC, diameter, and PR, we can see LIFO is the optimal policy, and clock is the optimal policy in TC algorithm. If LIFO over clock does not correspond to the optimal policy, the hit ratio is even lower than that of the random policy. On the other hand, in overall, GAG provides comparable or better performance to the optimal policy, as shown in the figure. Besides, GAG keeps track of data access patterns, switching policies as needed. So the figure on the right shows that the active policy transitions from clock to LIFO or LIFO to clock over time. So in some cases, GAG performs even better than the optimal policy. In these figures, we compare the amount of read and the execution time to those of the existing scheme. Compared to flash graph, which uses clock, GAG provides higher performance, especially for algorithms such as WCC, diameter, and PageRank. The amount of read decreased as more data was obtained from memory, and it led to shorter execution time. In particular, the effect was greater when using a slower device like SATA SSD. At the maximum, the execution time is improved by up to 65%. In short, existing cache policy reveals its ineffectiveness in graph applications, especially if the cache policy doesn't fit well with data access patterns. That's why we proposed GAG, graph adaptive caching, and it provides stable performance under variable graph workloads. GAG uses competition-based evaluation and grouping technique, and our experimental results prove its efficiency and potential. Thanks for your time.